Thank you. First, I want to thank the organizers for creating this great workshop and for giving me the opportunity to speak here. I'm going to tell you about delayed radio flares, and you already heard about this in the first day. Unfortunately, I had to miss the first day, and apologies for all the speakers. But before that, sorry, just a quick reminder that radio observations provide great diagnostics of TDEs. You heard this already, but just to briefly remind you, it can track the outflows, give you the information about the velocity of the outflows, measure Lorentz factors, give you information about the size of the emission region through brightness temperature or scintillations, information on the cooling processes that take place, whether it's a structured jet or not that you're seeing. Maybe you can get some info on the fraction of energy in the magnetic fields, and also indirectly it can give you some information on density structure and density variations in the close vicinity of the supermassive black hole. So a lot of great diagnostics via radio observation. This is just one example, switch A1644, that you all know of. Now, in the radio, until recently, that was the status of the field. You had many limits on the radio emission. You had a small number of events that are jetted with very bright radio emission, which you see on top there. And starting with 14 Li, observed by Kate and Short, we started seeing radio emission from thermal TDEs, not the jetted relativistic ones. And by now, there are a few examples like 19DSG and others, but that was sort of what we've known. And at that time, all of the radio emission detected so far, we believe that it's prompt emission. So it's originating from outflows that were launched briefly after the star is disrupted. That has changed with the discovery of delayed radio flares, beginning with 15 OI. So 15 OI was the thermal TDE detected in optical, and you can see sort of the same plot that I showed before with many limits or observations of other thermal TDEs like 14 Li that I mentioned. And 15 OI is presented in the red line. We had a few limits up to about 3 months after disruption. And then we took a chance on it and tried to observe it again after 6 months. And surprise, surprise, it was just flaring up at 6 months. And then it slowly evolved. I'll show you the evolution in the next plot. It slowly faded away. And then in Vilas data, we found that it's flared up again after 4 years. And I believe you heard about additional information about the secondary flare on the first day. So I won't go into that. I'll just focus on that initial delayed flare. So what did we find out? We triggered VLA right away. And this is the spectral evolution of this initial delayed flare, which was also odd. We can see the spectral peak. The optically thick side is rather shallow, actually. It's more like nu to the power of 1 instead of the power of 2 or 2.5 that you usually see in asynchronous self-absorption. And after 2 weeks, the peak flux slightly decreases, but the frequency doesn't evolve much, which is actually surprising. It's not, doesn't fit really the standard models. More surprisingly, after a month, it's becoming totally optically thin, and the peak frequency drops below the observed frequency. So this is unexpected based on models that are used to explain any of the jetted TDEs or the thermal TDEs like 14 Li, for example, or DSG. Also, it was already mentioned that it had X-ray emission that is slowly increasing. That was in a paper by Suvi and Yair. I'll show you that in a second. But we tried to find some explanations or something similar to what is observed here, and we found that this behavior of the peak flux and frequency in the radio is similar to what is seen in some blazar flares. Okay, so there may be a connection in terms of what is the explanation or what is the mechanism behind this behavior. So we should probe into that. I'm just suggesting direction to explore. I'm not saying that this is the explanation. Okay, we really don't have answers about those events. So this is the X-ray that I just mentioned. It's slowly increasing. This is the radio flare. Unfortunately, there is a big gap here in the X-ray emission. And you can see we already mentioned that in the paper, that the X-ray luminosity is crossing some threshold that is usually used in X-ray binaries. When you see flares in X-ray binaries, the luminosity increase beyond about 1% of the Eddington luminosity. So again, not suggesting that this is exactly the mechanism that is ongoing here, but just exploring another possibility or similarities to other events, and maybe we can learn from them about the mechanisms that are beyond this delayed radio flares. So maybe this is, we said that this is maybe a state transition of the accretion, but we don't really know. We do know that, by the way, that the shock in a jet model that is used in X-ray binary flares and also used in laser flares actually show this kind of transitions beyond the fraction of the Eddington luminosity. And there is a statistical evidence for this kind of things happening also in AGNs, but it's not observed in real time. So maybe we're seeing this in real time for the first time. Okay, so this was the first event in which we saw delayed radio flares, and you heard about many more in Vet's talk. And I want to move on to another event that was also covered, I believe, on the first day. This is 19 AZH, and this is the light curve observed by Amy, which is a radio observatory in the UK, observing at 15 gigahertz, and we can have very high cadence observations that you can see here. And we believe that there are two bumps here, right? As you can see, there is an initial prompt radio emission, and then there is another flare on top of this. And this is from Goodwin et al. Paper, and this is, I think, what you saw on the first day. This is on a much longer time scale of the evolution, so it keeps increasing in flux. And I suspect that if we had this kind of high cadence coverage with Amy throughout this long-term evolution, we might have seen these kind of bumps until the peak and then the decline. So our data is all the way up to here, but our data show that it's not really a monotonic rise, but simply this structure that you can see here. A flare that goes into sort of a plateau, and then another flare. Okay. If we look at the X-ray data from this event, this is the X-ray data from the X-ray is from Hinkle et al. And you see the luminosity and hardness ratio. You see that there was an X-ray flare just before what we call the delayed radio flare that we've observed with Amy. And also you can see that the hardness ratio changed from sort of intermediate state to a completely soft state during the X-ray flare. And then with a lag of about 100 days, there goes the radio flaring up. And again, this is something that we see in X-ray binaries, which are obviously totally different systems and totally different scales. But in X-ray binaries, you see this kind of scheme that describes the evolution in X-ray, in the luminosity and hardness ratio. We see something similar, but that is not exactly matching this cycle. Usually when X-ray binaries go through that, they go up and do this, and then they're stuck in this kind of a cycle here, flaring up again and again until they go down. And what we see matches more of these kind of subcycles, okay? But again, there is a gap in the observations. So again, just pointing similarities and not saying that this is exactly the same, but something to think about. All right, so as we heard already, Richard mentioned yesterday that there are a few TDEs that there have been suggestions for a state transition in the accretion state, and this is just one more example. Yvette talked about 18HYZ, which has a delayed radio flare of 4 years, right? Something like that. 2.5, okay. Sorry, 4 years is 15OI, yeah, 2.5. Incredible data set in multi-wave frequencies. And the analysis based on this data set suggests that maybe we're seeing a delayed ejecta. So this is also what we mentioned for 15LI, suggesting that maybe there is a delayed ejecta, but it's not really clear. Here it's a bit clearer case, I would say. But there is another suggestion. Matsumoto and Kiran suggested that maybe we're seeing an off-axis jet. And following that, my student Itai Sfaradi, together with Paz sitting here, applied this model to 18HYZ, including our own data set from Amy again, this beautiful dense light curve at 15 gigahertz. And we find that it actually can be explained by an off-axis jet, but again, this is not saying that this is what's happening. It's another possible explanation. And actually, Yvette, you told me that you have an additional few points here that maybe rule out these turnover, so we have to see about that. I'll be interested in seeing this. And maybe, Paz, you can maybe tweak the model as we usually do to fit that better. All right. So again, maybe some of these delayed radio flares are state transitions, maybe some delayed ejecta, maybe some off-axis jets. There are a few suggestions out there. Okay, we do know that an off-axis jet cannot explain the first initial delayed radio flare observed in 15 OI and in a few other cases. And I'll next show you a few other interesting cases not published just yet. This is one of them. And I'll be very interested to talk with theorists here in the audience to see if they have any new suggestions. So this is a case where you, again, these are all optically discovered TDEs. This is a case where we have a limit here, relatively late time, but you do what you can. And also a limit in the X-rays. And this is, again, data from Amy. Suddenly we see it rising and then plateauing for a long time. Okay? Then it's rising again, and then again it's plateauing, and it's still at that stage. Okay? We triggered SWIFT. We found that there is also a delayed onset of X-ray emission with a plateau here. So I don't know of any standard model of outflows that are ejected and can do this. So I'm open to suggestions. Before moving on, just showing you the very peculiar, I would say, spectra of this event. You can see the evolution in time, very shallow, optically thick emission, and very broad, flat, I wouldn't even call it a peak. Okay, so maybe more like AGN spectra, I don't know. But you do see evolution, right? You don't see this kind of evolution on these time scales in AGNs, I would say. This is another case. Nothing, nothing, nothing. Then it erupts, and it's still shooting up, actually. We're still following that. There is nicer information. Erin and her group are helping us with that. There is a lot of variability, daily variability in that data, and we're still following this. Still didn't try to model this actually, but we do have spectral information. And again, this is very odd. This is the most recent one, and it seems like even the peak frequency is going up a bit. okay? And again, very shallow here and very broad peak. Not what you expect based on the initial observations in the radio of TDEs, right? Like for 14 Li. All right, so those are a few interesting cases that show that the standard models really doesn't work. And we need new models, and even if you find a model that can explain, let's say, 18 HYZ, whether it's a delayed ejecta or an off-axis, we did some other model for the rest of them, because it's really a zoo, okay, of events. And they're very common, as Yvette's work showed. Roughly 40% of TDEs show very late time emission. The last ones I showed actually show delayed radio flares on timescales of 100, 200, 300 days. I have an intuition that maybe there's specific delayed radio flares that are ongoing on these timescales of 200 days, sort of, and then the ones that are flaring up on years timescales, like 3, 4 years. Maybe the very late ones are off-axis, but the initial ones are something else. Just my own personal guess. Again, something to discuss over the next few weeks. I want to finish up with this puzzling case. It's not a clear delayed radio flare. Okay? There is prompt radio emission, as you can see at the timescales here, prompt radio emission, and again, very high kindness observations that prove to be very important. When we look at around where the red line is, we sort of thought that we're seeing sort of a deviation from the decline that just started after the peak. So we actually increased the cadence of observations. And we saw that there is a slight deviation from the power law we got from the initial feed. And then it's also highly variable, as you see here. And you can show that this variability is statistically significant. It's not just noise or something systematic. Actually, you can see the variance of the phase calibrator here, and there is real variability on a time scale of, I would say, less than a day. Here, and then it stops, we think, but we don't have any additional data here. So what causes this maybe slight increase of radio emission and also the onset of daily variability for some period of time at late times? I don't know, okay? Maybe a jet picking up or something like that. Again, I'm throwing ideas because, as I said, we have mostly questions about this and no answers just yet. And one last thought. I'd like to show these slides for a long time, for a few years now, since I started working on radio transients in surveys, actually. When starting working on the Caltech transient surveys about a decade ago, I think, already, with Greg Hallinan and Kunal Muley. We found back then what we thought is a transient. Actually, it's not a transient here. In a red and dead galaxy that show no kind of feature of AGN or something like that. And when we found more and more transient, there are real transients, but again, I thought maybe some of the things we're actually seeing as compact, weak radio sources in radio surveys, usually people discussed the bright sources, but not the weak ones, are relics of old TDEs. I don't know, just a thought, something to think about and discuss, unrelated to really the delayed radio flares, but maybe related. So just to summarize, delayed radio flares are a common new phenomena. Their timescales range from sort of a half a year to a few years, and they can flare multiple times. It's really a zoo of events. As you've seen, there's diverse properties. Many of them don't match one with the other. There are many open questions, whether it's related to accretion, whether it's related to jets, off-axis jets, maybe, whether it's just delayed ejecta, related to a transition in the accretion state. Can there be any connection to late-time phenomena in other wavelengths? Maybe these infrared flares, or maybe neutrinos? I don't know. Can we learn something or try to find the answers by looking at other phenomena like AGN knot ejections that are used to explain the blazar flares, for example? Or maybe you look at X-ray binaries and learn something from that is applicable to those. And trying to just think about what we should do forward, I think that radio surveys actually, like VLAS and ASCAP VAST, will play a big role in finding more of these delayed radio flares, but we need to follow them up. And we really need the high cadence observation. That is, cannot be done. We need the spectral information. VLA does that, and other observatories do that. But we do need high cadence, and currently AMI, for example, can do that, but we need more observatories like AMI, and we tried to push this idea in a recent paper led by Rob Fender, myself, and others. So please go and think about this idea as well. And I'll conclude with that. Thank you.
Okay, any questions? Brian, go ahead.
So going back to that really rapidly variable jet.
Which one? This variability?
Yeah. So, I mean, an obvious thing is some type of, internal emission of a jet, right? So I guess I'm wondering, do you have any constraints? I guess looking at the spectra, do you have any constraints on the size of the emitting region, for example, from self-absorption that could constrain whether you can really get that kind of rapid variability? I mean, it could also be Doppler effects that make it more rapid than
right. No, we haven't. This is just an initial plot of this trying to fit the light curve from a couple of weeks ago, but we haven't tried any of that. I guess, you can say that if the variability time scale is less than a day, you can put a limit on the size through that, but not more than that.
I guess I'm wondering whether that's constrained also by the spectrum, by the self-absorption. Low frequencies, if you can use the self-absorption frequency to constrain the emitting region size.
If we would have had that information, that would have been great.
Okay, thanks.
But we don't, unfortunately.
Okay,
so I'm interested in the similarity between 15 OIs flare and the blazars you pointed out.
Yeah.
And the peak frequency moves very rapidly. And I guess in the case of blazar flares, the emission comes from internal shock. And,
basically, I based this statement on a paper by King et al. In a flare in M81, actually, and there is also another object, CTA 102. And they explain this as a jet in shock in a jet. There is an existing jet. You throw like a high Lorentz factor blob into that. Mm-hmm. And then that interaction within the jet creates this kind of a flare. But I also find out that if you look at the shock in a jet model, that is can be used to explain most of the data in radio flares in blazars and AGNs. There are certain phases of the flares in the data that are not actually explained by this model. And this specific transition, you can see this in the data, but it's not covered by the model itself.
Okay.
The rest of the phases are, but this is not. So
thank you.
This is another open question.
Erin?
I had a question about, I appreciate all of the ideas that are being put together in this zoo, and I'm still trying to get a sense of it myself. Is the claims of state transitions and these being related to state transitions, are those only coming mostly from the multi-wavelength, like when you see a X-ray versus when you see optical? And I'm asking because I'm thinking about X-ray binaries where we see state transitions and we get these radio ejecta happening during the state transition. The equivalent time scale, if you scale that to an AGN, is 1,000 years or something, right? So like maybe it doesn't necessarily, like I'm having a hard time making the connection between like, you know, seeing a state transition in the optical versus X-ray and then what you infer from the radio.
Yeah, I agree. So that's why you know, the asterisk there is similarities. So maybe we can learn something from that, but it's not applicable directly. As you say, if you just scale it up, it doesn't work, right, in terms of timescales. So, but I'm trying to see if, well, I'm not trying, but I'm just pointing out similarities in case we can take some parts of the physics from there and apply it in a new model here. I don't know.
Yeah.
But it is based basically on the X-ray and radio, I would say. Mm-hmm. In 1501I, it wasn't that clear because it was sort of a continuous rise, and we saw this increase about the fractional 1% in end-income luminosity, and you know, in the literature, this is sort of the threshold that is mentioned. Although some argue that it's more 10% and not 1%. So yeah. And so it was kind of just a mention. It was clear that it's gone completely soft in AZ age, 19 AZ age. Again, not saying that it's a state transition, but just saying that it's similar to what we see. I don't really have a clue. I didn't work on X-ray binaries at all. But I do wonder if we can borrow some things from there to that.
Yeah, definitely. I guess I would say, like, to me, it's more surprising that there is a connection between the state transition, like the corona to disk state transition. Like the fact that you see that the radio is correlated at all with this is more surprising to me, because I would expect that there would be some like massive delay of the radio. And so like just because you don't see that in some cases, you don't see a change in like the optical to X-ray during these radio flares, doesn't mean that it isn't related to a straight state transition. Right. Because I would expect huge delays. Yeah.
Yeah.
Okay, I have a quick question. You showed these, you know, very, very luminous X-ray flares and radio flares at late times. Is the optical just doing its happy plateau thing that Short showed us?
I think so.
Okay. So the optical is sort of uncorrelated with what the radio and X-ray are doing at late times.
I guess that maybe see a larger sample, so I don't know if you...
We're not seeing anything in the optical. We don't always see an X-ray correlation.
Yeah.
Thanks. Okay.
Yeah, thanks. My question is also about this source. I'm very excited to see the vast variability. And we also saw something like this, right, for Assassin 14Li on a slightly longer time scale, and we could correlate it with the X-ray and see this cross-correlation. So do you have any contemporaneous like X-ray data for this? Or
not for this, unfortunately for this, no.
But it could work, I guess, still. Yeah. So that would again point to this internal model again. Yes, it's exciting. Yeah. Or scintillation.
We should scintillation. No, I think it's 15 gigahertz. That's it's hard to do that. Okay. But
you can still do it.
You can still do that. Okay.
But does it? If it's expanding, it would be strange that it turns on at late time, right? Yeah. So.
All right.
So my question was on the flares too, but not on the very fast, like on the other thing you said. So do you have any idea what kind of brightness temperatures we're talking about during those flares?
No, I didn't. We didn't do that.
Okay, but you can do it.
Yeah.
Like you have the sizes.
Yeah.
Okay.
It's not. It's like thermal emission. It's not in terms of not being. There's no compactness issue or something like that.
No, but if you have a jet, which is one of the scenarios.
I don't think the jet scenarios will work for that.
Oh yeah, but I was not talking about the specific one. I'm just generally when you see these flares, can you measure brightness temperatures? And if
we can do this calculation, but I haven't done this.
Okay, we have time for one more question, and then we'll have lots of time at the afternoon break.
Okay.
If it's a quick question.
Yeah, just a comment on the 19 AZ age.
Yeah.
We got a XMM spectra at early times and late times.
Okay.
And like the hardness ratio is not like a straight transition like in X-ray binaries where you have the corona forming.
Okay.
Is just the temperature of the soft component that is changing.
Okay.
It's hotter at early times. That's why it looks harder, but it's not the same hardness as like in a corona forming. So there's never a corona in the source. It's always, I mean, it's very faint, maybe a very faint parallel, but it's always thermally dominated.
Okay. I'll be
So that's
interested in looking into that. Okay. Let's discuss this. Great. Thanks.